Picture a man who travels into his own past to prevent a single event. He has the means, the moment, every intention, and he fails. Not because a guard stops him, not because his nerve breaks. At the instant of action, the weapon jams, or his hand slips, or some small accident intervenes. Every path that would rewrite the past closes, quietly, as if reality were curating the outcome. This is not a plot device, it is a physical conjecture, written in the language of Einstein's equations, that assigns to any history-changing event a probability of exactly 0. In 1990, a group of physicists led by John Friedman, with Kip Thorne and Igor Novikov among them, stated it formally. The only events that can happen are the ones that remain globally self-consistent. Paradox is simply never permitted to occur. The idea is called the Novikov self-consistency principle, and it points somewhere stranger than time travel itself. It points to a universe that, if it is a fixed four-dimensional block, was always whole, always finished, structurally incapable of contradicting itself. By the end of this video, you will understand what a closed time-like curve is and why general relativity permits one. How the Novikov self-consistency principle forbids paradox without any force, why the rival models of David Deutsch and Stephen Hawking disagree, and what a universe that cannot contradict itself suggests about whether its consistency is accident or signature. If you find value in explorations like this, in understanding the deep puzzles that keep physicists awake at night, consider subscribing to the channel, which helps these deep dives reach more curious minds. Now, let us begin. To understand why a principle like this was ever necessary, we have to start with a fact that surprises most people who hear it for the first time. General relativity, our best and most precisely tested theory of gravity and time, does not forbid time travel into the past. It permits it. Not as a loophole, not as a fringe speculation, but as a class of exact solutions to Einstein's field equations. The technical name for a path into the past is a closed time-like curve. The phrase sounds forbidding, so let us take it apart. A world line is the track an object traces through spacetime, moment by moment. A time-like world line is one that always moves slower than light, the only kind of path a massive object like you or a spaceship can follow. The word closed is the strange part. A closed time-like curve is a world line that is everywhere future-directed, always moving forward in local time, always slower than light, and yet which loops back and reconnects with its own past. At no point does the traveller exceed the speed of light. At no point does the traveller feel time running backward. Locally, everything is ordinary. Globally, the path is a loop. Follow it far enough into your own future, and you arrive at your own past. This is the first thing the research forces us to hold clearly. The Novikov self-consistency principle is not a claim that time travel is easy or even possible to build. It is a claim about what would be allowed to happen if a closed time-like curve existed. And closed time-like curves are not invented for the sake of argument. They fall out of the mathematics on their own, in solution after solution, going back nearly a century. The first appeared without anyone recognizing what it was. In 1924, the mathematician Cornel Lanczos wrote down a solution describing rotating dust, a cloud of matter spinning about an axis. In 1937, the Dutch physicist Willem van Stockum analyzed the same kind of object, an infinite, rigidly rotating cylinder of dust, and the solution contained closed time-like curves, though their significance went unnoticed at the time. The rotation drags the very structure of space-time around with it, tilting the light cones, the local definitions of past and future, until far enough out, the future folds back into the past. And Van Stockum's cylinder was not a one-off. Closed time-like curves have a habit of turning up, uninvited, across solutions that share nothing else in common. They appear inside the rotating black holes described by the Kerr metric, the most realistic black holes we know of, lurking in the deep interior beyond the horizon. They appear in the space-time of two infinitely long cosmic strings sliding past one another, a configuration the physicist J. Richard Gott analyzed in 1991. They appear wherever matter rotates hard enough or space-time is twisted sharply enough that the local sense of forward in time can be tipped all the way around. This is the uncomfortable fact the research keeps underscoring. Loops in time are not a single exotic loophole that one clever fix might seal shut. They are a recurring theme in the deep structure of general relativity, surfacing again and again in solution after solution, as if the theory keeps trying to tell us something we would rather not hear. The solution that made the physics community pay attention came in 1949, and it came from one of the most rigorous minds of the 20th century. Kurt Gödel, the logician who had shaken the foundations of mathematics with his incompleteness theorems, turned his attention to relativity. At the Institute for Advanced Study in Princeton, as a gift for Albert Einstein's 70th birthday, Gödel presented a new solution to the field equations, an entire universe, rotating, homogeneous, the same at every point, and not expanding. Inside Gödel's universe, the light cones tilt progressively as you move outward, until, beyond a critical radius, the time-like paths curve back on themselves. Because the universe is homogeneous, the same everywhere, this is true at every point. There is a closed time-like curve passing through every single event. In Gödel's universe, the past is, in principle, reachable from anywhere. Einstein, receiving this as a birthday present, was unsettled by it. The solution was mathematically flawless. It simply described a universe in which the distinction between past and future, the bedrock of causation, dissolved. Our own universe is expanding, not rotating in the way Gödel's was. So his particular cosmos is not ours. But the point had been made, and it could not be unmade. The equations of general relativity, left to their own logic, permit histories that loop. Gödel drew a conclusion from his own solution that went further than most physicists were willing to follow. If, in a universe permitted by relativity, one could, in principle, travel to any past moment, then the past has not truly elapsed. It is still there to be reached. And if whether a moment counts as past depends on an observer's path through spacetime, then the lapse of time, the passing of the now into the gone, cannot be an objective feature of reality. Gödel took his rotating universe as evidence that time, as we live it, is in some sense ideal rather than real. The most rigorous logician of the age had placed himself alongside those who hold that the flow of time is an appearance, not a fact. To picture what his rotating universe does to cause and effect, consider a fast carousel dragging the air and dust around it. Stand at the center and the world stays orderly. Walk outward and the spinning floor pulls your sense of straight ahead around with it, until the direction you call forward bends into a circle. In Gödel's cosmos, the spinning is not of air, but of space-time itself. And what gets dragged is not your footing, but your future. Far enough out, forward in time curves into a closed ring. The light cones, the local maps of what counts as later, tip over so far that later becomes earlier, smoothly, with nothing ever moving faster than light. What does it mean that the most successful theory of time we have ever written contains, in its own exact solutions, paths that lead into the past? Hold that question. We are only at the beginning. After Gödel came others. In 1974, the physicist Frank Tipler analyzed a massive, infinitely long cylinder spinning at tremendous speed. The research is specific about the numbers. To twist spacetime into closed time-like curves, the Tipler cylinder would need a total mass exceeding 10 times that of the Sun, densities approaching those of a neutron star, and a surface spinning so fast that it moves at a sizable fraction of the speed of light, exceeding roughly half of light speed at the relevant radius. Spin a cylinder of that mass and density fast enough, and the frame dragging becomes so severe that a traveller circling it can return to their own past. Then, in 1988, the topic moved from cosmic exotica to something that felt, briefly, almost engineerable. Kip Thorne and his students at Caltech, Michael Morris and Ulvi Yurtsever, published a pair of papers on traversable wormholes. A wormhole is a tunnel connecting two separated regions of space-time, a shortcut through the cosmic geography. Morris and Thorne showed that if you could hold a wormhole open and then move one of its mouths at high speed, or place it in a strong gravitational field so that the two ends aged differently, the wormhole would become a time machine. Enter one mouth and you exit the other, not just elsewhere in space, but elsewhere in time. The mathematics of holding that tunnel open is captured in the Morris-Thorne wormhole metric, which describes the geometry of the throat. Written out, it reads ds squared equals minus e to the 2 phi times c squared dt squared plus dr squared over 1 minus b of r over r plus r squared times the angular part. The function phi is called the redshift function, and it must remain finite everywhere so that the wormhole has no horizon, nothing that would trap a traveller. The function b is the shape function, which sets the geometry of the throat. The point of the equation for us is not the symbols, it is the consequence. When Morris and Thorne worked backward from the geometry they wanted to the matter that would be required to produce it, the matter came out wrong, or rather, exotic. This reverse engineering is worth pausing on, because it is the master move of the whole subject. Einstein's field equations, the heart of general relativity, can be written compactly as g mu nu plus lambda g mu nu equals 8 pi g over c to the fourth times t mu nu. On the left sits the geometry of spacetime, its curvature, captured by the Einstein tensor g mu nu, with lambda, the cosmological constant, and g mu nu, the metric. On the right sits the matter and energy, written as the stress-energy tensor T mu nu, with g, the gravitational constant, and c, the speed of light. Normally, you read the equation from right to left, specify the matter, and the geometry tells you how space-time curves. Morris and Thorne read it the other way. They wrote down the curving geometry they wanted, a throat held open, and let the equation tell them what matter must sit on the right to produce it. The equation complies without complaint. It simply hands back a stress energy that no ordinary matter can supply. Every time machine in this story is built by this single trick. Demand the geometry and read off the exotic matter the demand requires. To hold a wormhole throat open against its own tendency to collapse, you need matter that violates what physicists call the weak energy condition. Stated formally, the weak energy condition says that the quantity T alpha beta mu beta is greater than or equal to 0 for every timelike observer. In plain language, it says that the energy density of matter, as measured by any normal observer, is never negative. Ordinary matter obeys this without exception. A wormhole time machine requires the opposite, a region where the energy density is negative, matter that weighs less than nothing. This is the exotic matter the research keeps returning to. Whether the universe permits enough of it in the right configuration to build a working time machine is unknown. The mainstream view is skeptical. But the equations permit the construction. And once you permit the construction, you inherit the paradox. Negative energy is not pure fantasy. Nature provides it in tiny and fleeting amounts. Place two uncharged metal plates a hair's breadth apart in a vacuum, and the space between them holds fewer of the quantum vacuum's fluctuations than the space outside. The region between the plates therefore carries less energy than empty space itself, which is to say, negative energy measured against the ordinary vacuum. This is the Casimir effect, confirmed in real laboratories. The amounts are minuscule, nowhere near what a wormhole throat would demand, and whether they can be concentrated and held on the scale a time machine requires is precisely the open question. But the door is not bolted shut. The energy condition that ordinary matter never breaks, the quantum vacuum bends just slightly. Think of the weak energy condition as a floor that all normal matter stands on, a floor below which energy density never drops. The Casimir effect is the discovery that the floor has a trap door, narrow and shallow, but real. A traversable wormhole asks whether that trap door can be widened into a doorway. No one knows. But the asking is legitimate physics, not fiction. Here is the paradox in its oldest and bluntest form. Suppose a traveller goes back and kills his own grandfather before his parent is conceived. Then traveller is never born. Then there is no one to make the trip. Then the grandfather is never killed. Then the traveller is born after all and goes back and kills the grandfather. The chain of reasoning eats its own tail. Logicians call it the grandfather paradox. For most of the 20th century, it was treated as proof that time travel into the past must be impossible. The reasoning was simple. Time travel leads to contradiction. Contradiction is impossible, therefore time travel is impossible. But general relativity would not cooperate. The solutions kept appearing. Gödel, Van Stockham, Tipler, Morris and Thorne. The equations said the geometry was allowed. So the question sharpened into something more uncomfortable. If a closed time-like curve can exist, the real issue is no longer what is forbidden in principle, but what actually happens physically when a traveller tries to create a paradox on one at the very moment of the attempt. This is the question that the Cauchy problem makes precise, and it is worth understanding why it matters. In ordinary physics, you specify the state of a system at one moment, the positions and motions of everything, the configuration of every field, and the laws of physics evolve that initial data forward in time uniquely. Give the present, and the equations hand you the future. This is called the initial value problem, or the Cauchy problem, named for the mathematician Augustin-Louis Cauchy. It is the deep reason physics can predict anything at all. Closed time-like curves break this. There is a surface in such a space-time called the Cauchy horizon or chronology horizon, which marks the boundary between the ordinary region, where the past does not loop, and the region where it does. Cross that horizon and the neat machinery fails. Initial data on an earlier surface no longer determine the evolution uniquely, because events in the looping region depend on themselves. The future is feeding back into its own past. The question of what is consistent stops being a philosophical worry and becomes a mathematical one. Given a space-time that loops, the task becomes determining which physical histories are even well defined on it. Picture the difference as two ways of running a film. Ordinary physics is a projector threading a reel forward, each frame fixing the next, the ending implicit in the opening the moment the projector starts. A spacetime with a closed timelike curve is a reel whose final frames have been spliced back onto its own beginning, so that the last scene is also physically part of the first. Run that loop, and the question is no longer what comes next. The question is whether the whole spliced reel tells a coherent story at all, whether there exists any complete film in which every frame agrees with every other. Most splicings would produce nonsense, a hero alive and dead in the same instant. The Novikov principle is the claim that only the coherent films are ever screened. What does it mean that the deepest reason physics can predict anything, that the present fixes the future, is exactly the thing a loop in time quietly takes away? It was into this precise question that Igor Novikov stepped. Novikov, born in Moscow in 1935, is one of the major figures of 20th century astrophysics. He proposed the existence of white holes in 1964. He headed relativistic astrophysics at the Soviet Space Research Institute. And in books written in 1975 and 1983, he offered a quiet, radical opinion about time loops. The closing of time curves, he wrote, does not necessarily imply a violation of causality, since the events along such a closed line may be all self-adjusted. Self-adjusted. The events on the loop do not contradict each other because the only loops that exist are the ones whose events already fit. That intuition received its formal statement in 1990, in a paper titled Cauchy Problem in Spacetimes with Closed Timelike Curves, published in Physical Review D. The authors were John Friedman, Michael Morris, Igor Novikov, Fernando Echeverria, Gunnar Klinkhammer, Kip Thorne, and Ulvi Yurtsever, a roster that includes much of the field at once. Their central statement is precise, and the research preserves it. The only solutions to the laws of physics that can occur locally in the real universe are those which are globally self-consistent. A local solution, something happening in one small region, is permitted only if it can be extended to a complete global solution that is well defined everywhere. We can state the principle in its formal shape. A local solution is allowed if, and only if, it forms part of some global solution that is self-consistent across all of space-time. Speakable, it is just this. A local event is allowed only if it extends to a globally consistent whole. There is no force in this. There is no agency. The principle does not say that something reaches in to stop the traveller. It says that the histories which contain contradictions are not part of any complete, consistent solution, and so they are not among the histories that occur. The probability assigned to a paradox-producing event is not small. It is exactly 0. Sit with how strange that is. The traveller who tries to kill his grandfather is not battling a guardian. He is attempting to walk a path that, examined globally, does not close. And in the Novikov picture, paths that do not close are simply not walked. Something will intervene, not because the universe wants it to, but because the only version of events that exists is the one in which the intervention happens. The gun was always going to jam. The slip was always part of the story. To make this concrete, the physicists needed something simpler than a grandfather. They needed a clean mechanical paradox, and they found it in a billiard ball. The setup came to be called Polchinski's paradox, after the string theorist Joseph Polchinski, who proposed it. Polchinski imagined a billiard ball rolling toward a wormhole time machine. It enters one mouth, travels back in time, emerges from the other mouth in the past, and strikes its own earlier self, knocking that earlier self off course so that it never enters the wormhole in the first place. A grandfather paradox with no grandfather, no free will, no consciousness to complicate it, just a ball, a wormhole, and a contradiction. Polchinski, in his own memoir, was wry about it. The Polchinski paradox, he wrote, a science fiction motivated idea for which I wrote no papers, seems to be my claim to fame. He sent the problem to Kip Thorne. Thorne, by his own account, got excited, and he set two of his Caltech students, Fernando Echeverria and Gunnar Klinkhammer, to find out what actually happens to the ball. What they found is the heart of the matter. They could not construct the paradox. Every time they try to set up a trajectory in which the ball knocks its earlier self completely out of the wormhole, the global solution refused to close. But they could always find a different solution, a self-consistent one. In these, the returning ball does not knock its earlier self away entirely. It delivers a glancing blow, a softer strike that alters the earlier ball's path just enough to send it into the wormhole at a slightly different angle, so that it returns and delivers exactly that glancing blow. The story closes. The ball's whole journey is consistent with itself. The collision that seemed to create the paradox turns out to be the very thing required to produce it. The viewer should pause here. Before we continue, consider what this means. The self-consistent solution is not a near miss or a compromise. It is a complete history in which the time-travelling ball causes the exact deflection that sends it back to cause that deflection. Cause and effect form a closed ring with no loose end. Nothing was prevented. Nothing was changed. Everything simply fit. But the research records something that troubled even the people who found it. Echeverria, Klinkhammer and Thorne discovered that for a given initial trajectory of the billiard ball, there was not one self-consistent solution. There were many. In fact, for every starting condition they examined, they found a whole family of consistent extensions, and later work suggested the number could be infinite. Every toss of the ball admits infinitely many self-consistent histories, and the classical physics contains no rule whatsoever to say which one actually happens. Keep that number in mind. Infinitely many consistent histories and no law to choose between them. We will return to it, because it is one of the deepest cracks in the whole structure. And it points somewhere the equations alone cannot follow. There is one more idea we need on the table before we go deeper, because it reframes everything that follows. The Novikov self-consistency principle sits naturally inside a particular picture of time, the one philosophers call eternalism, and physicists associate with the block universe. On this view, which flows from the way relativity treats space and time as a single four-dimensional structure, the past and the future are not gone and not yet to come, they simply are. The whole of history, every event that has ever happened or ever will, exists together as a fixed four-dimensional block. The passage of time, the sense that the now is moving, is, on this reading, a feature of conscious experience rather than of the structure itself. Notice what the block universe does to the grandfather paradox. If the past already exists, fixed, as real as the present, then it was never an open question whether the grandfather lives or dies. Whatever happened on that closed, time-like curve is simply part of the block, already there, already whole. You cannot change the past on this view, not because a force stops you, but because there is no separate, malleable past to change. There is only the one consistent, four-dimensional whole, and your trip into it was always one of its threads. Some who hold this view draw a sharp conclusion from it about freedom, and about whether a history fixed in this way leaves any room for genuine choice, or for any purpose directing it. We will return to that conclusion in due course, because it reaches well beyond physics, and it does not survive the examination as cleanly as its defenders assume. To hold the block universe in mind, picture the whole of time as a loaf of bread. Every slice is a moment. The slice at one end is your birth, the slice at the other your death, and all of them are equally there, equally real, the loaf complete. What you experience as the passing of time is, on this view, something like a knife moving down the loaf, lighting up one slice as now, then the next. But the knife adds nothing. The slices were always there. The block universe has corridors of its own, which we have walked elsewhere. Here it is only the stage on which the loop is set. The physicists who formalized self-consistency saw this implication and stated it plainly as part of the mathematics. In their 1990 paper, Friedman and his colleagues wrote that any being who went through a wormhole and tried to change the past would be prevented by physical law from making the change, and that the free will of the being, as they put it, would be constrained. They were careful, even cautious. They added that it was not obvious to them that this constraint is any more severe than the constraints physical law already imposes on all of us every day. You cannot will yourself to fall upward. You cannot will yourself through a solid wall. On their telling, the inability to change the past is one more limit of the same ordinary kind. Whether that is all it is, we will weigh later. What does it mean that the principle which forbids paradox is, at bottom, a statement that the past is as fixed and as finished as the floor beneath your feet? For now, hold the picture as the researchers present it. A universe whose equations permit loops in time. a principle that allows only the loops that close. A billiard ball whose paradox dissolves into a glancing blow. And a four-dimensional block in which, perhaps, the loop was always closed, because the whole of it was always already there. The classical picture, Novikov's picture, treats the time traveler as a single object on a single history. But the world is not classical. It is quantum. And when physicists carried the closed Timelike curve into quantum mechanics, the paradox did not simply dissolve. It split into rival resolutions that disagree with each other to this day. The most influential came in 1991 from the British physicist David Deutsch, one of the founders of the quantum theory of computation. Deutsch asked what happens when a quantum system, rather than a billiard ball, traverses a closed Timelike curve. His answer reframed the entire problem. A quantum system is described not by a definite state, but by a density matrix, a mathematical object that captures probabilities and mixtures of possibilities. Deutsch proposed that a system on a closed Timelike curve must satisfy a consistency condition. The quantum state entering the loop must equal the state coming back around it. The loop must reproduce its own input. Written formally, the Deutsch consistency condition reads rho c t c equals the partial trace over A of U times the quantity rho A tensor rho c tc times U dagger. Let us translate it. The term rho ctc is the quantum state of the time-traveling system, the part that goes around the loop. The term rho A is the state of the ordinary chronology-respecting world it interacts with. U is the unitary operator describing their interaction, the physics of the encounter, and U dagger is its mirror image required by quantum mechanics. The partial trace over A is a mathematical operation that averages out the external world to leave only the time traveler's state. The whole equation says one thing: the state that loops must return to itself unchanged by the round trip. Here is what makes Deutsch's move powerful. He proved, using a mathematical argument about the space of all density matrices, that such a self-reproducing state, a fixed point, always exists. No matter what interaction you set up, no matter how paradoxical it looks, there is always at least one quantum state that closes the loop. The grandfather paradox does not produce a contradiction. It produces a mixed state, a 50-50 quantum blend in which the traveler half kills and half spares, a superposition that loops back on itself consistently. Deutsch, writing with the philosopher Michael Lockwood in Scientific American in 1994, put the upshot plainly. Common sense, they wrote, may rule out such excursions, but the laws of physics do not. Think of it like tuning a guitar string to a room that echoes its own note back. You pluck, the room answers, and you adjust until the note you play and the note returning are the same pitch, locked, stable, self-sustaining. Deutsch showed that for a quantum system on a time loop, such a self-consistent pitch can always be found. The paradox is not silenced by force. It is tuned into a standing wave that feeds itself. Deutsch's resolution comes at a price that should make any physicist uneasy, and the research is candid about it. To force the loop to close on a fixed point state, Deutsch's equation must be nonlinear. It bends one of the most fundamental rules of quantum mechanics, the rule that quantum evolution is linear, that states combine cleanly. Break that rule and strange powers appear. A traveller on a Deutsch loop could, in principle, make perfect copies of an unknown quantum state, defeating the no-cloning theorem that ordinary quantum mechanics treats as inviolable. They could perfectly distinguish quantum states that are supposed to be indistinguishable. The loop becomes a kind of impossible engine, performing what the rest of physics forbids. And then comes the sharpest critique of all, one to hold in mind through everything that follows. In 2018, and again in 2021, the mathematical physicists Jürgen Tolksdorf and Rainer Wirch examined Deutsch's consistency condition and found something deflating. The very fixed-point equation that was supposed to be the signature of time travel can be satisfied, to any precision you like, in perfectly ordinary quantum systems with no closed time-like curve anywhere, and even in classical statistical mechanics, the physics of steam and gases. The condition that the 2014 photon experiment supposedly validated is not, it turns out, unique to time travel at all. It is generic, which means the laboratory analogue may have demonstrated nothing about real closed time-like curves. And the announcements that time travel had been simulated in the lab were claiming far more than the mathematics can bear. Keep that caution close. We will need it. This was not left as pure theory. In 2014, a team at the University of Queensland, Martin Ringbauer and colleagues with Timothy Ralph, built a photonic simulation of a Deutsch closed time-like curve, published in Nature Communications. They used two entangled photons, one playing the role of the time traveller's earlier self, the other its returning future self, interacting as Deutsch's model prescribes. The research preserves their own description. The scheme requires only a two-photon source for its demonstration, and its success probability is 1 in 9. They did not build a time machine. They built a laboratory analogue using quantum entanglement and a technique called post-selection that obeys the same self-consistency mathematics. And it showed something startling. Under Deutsch's rules, the no-cloning theorem, the deep quantum law that forbids making a perfect copy of an unknown state, can be circumvented. A real closed time-like curve, if Deutsch is right, would let you clone the unclonable. Pause on that, because overturns something physicists treat as bedrock. The no-cloning theorem is not a minor rule. It is one of the load-bearing walls of quantum mechanics. The reason quantum information cannot be secretly copied. The reason quantum cryptography can be secure. The reason the quantum world cannot be backed up like a file. And a single closed time-like curve, in Deutsch's account, would knock that wall down. It would let you take an unknown quantum state and produce a perfect duplicate, a thing the rest of physics declares flatly impossible. Whether that is a reason to believe such loops cannot exist, or a hint at powers we have never imagined, no one can say. But it shows how deep the disturbance runs. A time loop does not merely bend the rules of cause and effect. It reaches into the foundations of quantum theory and loosens a stone the rest of the structure was leaning on. A separate experiment, run in 2011 at the University of Toronto by Seth Lloyd, Ephraim Steinberg and collaborators, took a different route. It used a rival model, the post-selected closed timelike curve, developed by Lloyd and Lorenzo Marconi. In their words, the experiment tests what happens when a photon is sent a few billionths of a second back in time to try to kill its former self. The photon, like the billiard ball, cannot succeed. The only runs that survive are the consistent ones. What does it mean that two laboratories, using two incompatible models of time travel, both found that nature permits the loop only when the loop is consistent? It means the self-consistency is robust across the disagreement. But the disagreement itself matters enormously, and we must be honest about it. Deutsch's model and the Lloyd-Marconi model are not two descriptions of the same thing. Deutsch's model maps pure states into mixed states and is mathematically nonlinear, breaking one of the most basic features of standard quantum mechanics. The Lloyd-Marconi model maps pure states to pure states and is built on post-selection. They make physically different predictions. Physics does not yet know which, if either, is correct, and the experiments tested the models, not reality, because no real closed timelike curve was anywhere in either lab. The post-selected model carries its own troubling baggage. Timothy Ralph, one of the architects of the photonic experiments, noted that when entanglement is added, the post-selected closed timelike curve can allow signals to be sent to times before the loop was even created, and it reopens in a new form the Bootstrap problem of information with no source. Each resolution, examined closely, trades one strangeness for another. Deutsch buys consistency with nonlinearity and cloning. Lloyd and Marconi buy it with post-selection and signaling into the deep past. Novikov buys it with a global constraint and infinitely many unselected histories. There is no free lunch here. Every door out of the paradox opens onto a stranger room. And a quieter constraint runs through all of them, one with a peculiar flavor. Under self-consistency, information from the future can never be used to change the future, because any use that altered events would break the loop. The research draws the consequence to its sharpest point. Knowledge from ahead, if it arrives at all, must be either useless for changing anything, or so ambiguous and garbled that it is correctly understood only after the fact, once the moment it might have altered has already passed. The universe on this picture is permitted to whisper its future to you. It is simply never permitted to let the whisper matter in time. What does it mean that a consistent universe could contain genuine prophecy, and yet guarantee that the prophecy can never be acted on to change what it foretells? There is a consequence of Deutsch's model so extreme it reads like fiction, yet it sits in the peer-reviewed literature. If closed timelike curves existed and behaved as Deutsch describes, they would be computational miracles. In 2009, the computer scientists Scott Aaronson and John Watrous proved that a computer with access to such a loop could solve an entire class of staggeringly hard problems, the class called PSPAC, in a trivial amount of time. Problems that would take an ordinary computer longer than the age of the universe would be solved at a stroke. The loop does the work by finding its own consistent answer. There was a name for this trick before the physicists formalized it: time loop logic, a phrase from the roboticist Hans Moravec. The idea is almost obscene in its efficiency. To solve a fiendishly hard problem, you guess an answer, send the guess back in time to before you began, and arrange the machinery so that the loop is self-consistent only if the guess was correct. Wrong guesses would produce a contradiction, and so, by Novikov's rule, they never happen. The only history that closes is the one in which the right answer was sitting there from the start, appearing, as Moravec put it, by an extraordinary coincidence, immediately and steadily. The computation does not search. The answer simply is the answer, because no other answer is consistent. Take a moment with that, because it is genuinely vertiginous. In a universe with usable time loops, the hardest computations in mathematics would not be performed at all. They would be discovered already finished, the solution delivered by the only history that hangs together. Effort collapses into consistency. The labor was never necessary because the loop only ever closes on the answer. And this is where the physics brushes against something it cannot quite name. Aaronson and Watrous noticed the oddity themselves and stated it with unusual candor. It might be thought mysterious, they wrote, that nature finds a fixed point. How does nature do this? Does nature not have to find the consistent state before the computation starts, so that in some sense running the computation is not even necessary? And then their telling admission. While these issues are admittedly mysterious, to us they are not more mysterious than the starting assumption that closed timelike curves exist. Keep that phrase. Nature finds a fixed point. We will return to it, because the language hides an assumption that does enormous work, and that the physics never earns. The mathematics that makes the consistent answer well-defined is the sum over histories, the same path integral method Richard Feynman built quantum mechanics on, but restricted. Written compactly, the amplitude is the sum over only the self-consistent histories of e to the I s over h bar, where s is the action of each history and h bar is the reduced Planck constant. In ordinary quantum mechanics, you sum over all possible histories. On a closed timelike curve, you sum only over the histories that close. Friedman and Thorne and their collaborators showed that this restricted sum yields unique, well-defined probabilities for each consistent extension. The inconsistent histories contribute nothing because they are not in the sum. The paradoxical futures are not destroyed. They were never included. There is an even more elegant version of this idea, and the research highlights it because it removes the sense that self-consistency is an extra rule bolted on by hand. In 1995 and 1996, Andrei Carlini, Valery Frolov, Mikhail Mensky, Igor Novikov and Harold Soleng studied a particle traveling through a wormhole and interacting with its own past self. And they asked which trajectory it actually follows. Their result? The only possible trajectories that minimize the classical action, the standard quantity that all physical motion extremizes, are precisely the ones that are globally self-consistent. The principle of self-consistency, they concluded, is a natural consequence of the principle of minimal action. Read that carefully. Self-consistency is not an extra commandment. The paradoxical paths simply are not the paths of least action, and so the universe, which already follows least action everywhere else, does not follow them here either. Consistency falls out of physics we already had. Not everyone believes the universe even reaches this point, because not everyone believes closed time-like curves can form at all. The most famous objection came from Stephen Hawking in a 1992 paper in Physical Review D titled The Chronology Protection Conjecture. Hawking proposed that the laws of physics conspire to prevent closed time-like curves from ever forming on macroscopic scales, keeping the universe, as he put it, safe for historians. His proposed mechanism was quantum. As a region of space-time approaches the moment of becoming a time machine, at the Cauchy horizon, the quantum vacuum fluctuations pile up. Formally, the renormalized expectation value of the stress-energy tensor, the quantity that tells gravity how much energy is present, diverges, races toward infinity at the chronology horizon. Valery Frolov, separately, Sungwon Kim with Kip Thorne, had calculated this divergence in 1991. Hawking's argument was that this runaway energy would feed back through gravity and destroy the would-be time machine at the instant of its creation. The universe self-censors. Hawking stated his conjecture with his characteristic wit, and the research preserves both halves. It seems, he wrote, that there is a chronology protection agency which prevents the appearance of closed time-like curves, and so makes the universe safe for historians. And he added an argument that is half a joke and half deadly serious. There is also strong experimental evidence in favor of the conjecture from the fact that we have not been invaded by hordes of tourists from the future. The tourists' argument is funnier than it is decisive, and Hawking knew it. It assumes that if backward time travel were ever possible, at any moment in the entire future of the universe, someone would eventually use it to visit our era, and we would notice. But a wormhole time machine can only carry a traveler back as far as the instant the machine was first switched on, never earlier. No such machine has been built anywhere in our past. So, on its own terms, the argument predicts exactly the silence we observe, whether or not chronology protection is true. It is an argument shaped like evidence that, examined, settles nothing. Hawking offered it with a smile, and the smile was the point. But here, the honest account must record that the case is unsettled, even by its own author. Hawking later conceded that the back reaction of vacuum polarization does not necessarily enforce chronology protection. The physicist J. Richard Gott documented this concession, which traces to work by Michael Cassidy and Hawking himself in 1998. And in 1996, Li-Shin Li had already shown that introducing absorbing material between the wormhole mouths could smooth the vacuum fluctuations so that the stress energy stays finite at the horizon, leaving the time machine potentially stable. The divergence that was supposed to save the universe from time loops may not diverge after all. The physicist Matt Visser, surveying the whole battlefield, suggested the universe relies not on one mechanism, but on many overlapping ones. The universe, he wrote, appears to exhibit a defense-in-depth strategy. For appropriate parameter regimes, Casimir effects, wormhole disruption effects, and gravitational back reaction effects all contribute to the fight against time travel. Whether any of them is decisive, no one can yet prove. The full resolution, the research repeatedly notes, awaits a complete theory of quantum gravity. That does not exist. Now we arrive at the strangest object in this entire landscape, and the one that will matter most when we turn to examine the claims being made. It is not the grandfather paradox. It is its quiet opposite, and it is called the Bootstrap paradox, or the ontological paradox. Consider a self-consistent loop that contains information. A traveler reads a proof of a theorem in a book, carries it into the past, and dictates it to the mathematician who will later write the book the traveler read it from. The proof is correct. The loop is perfectly consistent. No grandfather is harmed. And yet, ask the simple question: who first discovered the proof? The answer is no one. The information exists because it exists. It was never created. It has no origin. The same can be said of an object, a watch, handed from a future self to a past self, who will grow up to hand it back. A watch that was never manufactured, looping through time, uncaused. Fiction reached this idea before physics did, and reached it most purely in a 1959 story by Robert Heinlein called, fittingly, All You Zombies, in which a single person, through a sequence of time travel operations, turns out to be their own mother, their own father, and the agent who recruited themselves. An entire family tree collapsed into one individual with no ancestors at all outside the loop. The story is a curiosity. The physics is not. The Russian physicist Sergei Krasnikov has argued that such self-created objects, sometimes called jinn, after the spirits said to appear from nowhere, are no less physical than ordinary things. Ordinary objects in cosmology, he points out, also appear only from either infinity or a singularity, from a boundary we cannot interrogate. Why is a thing that appears from a consistent loop any worse off than a thing that appears from the Big Bang? It is a fair challenge, and we will answer it. But notice, even in the neutral telling, the seams of strain. The research records that the bootstrapped loop appears to violate the conservation of information, a principle quantum mechanics holds nearly sacred, and to run against the second law of thermodynamics, which says that ordered structure, a proof, a watch, a complex pattern, does not assemble itself for free. A self-existent watch is not merely philosophically odd. It sits in tension with two of the deepest accounting rules in all of physics. The proponents of the origin-free loop tend to mention this quietly, if they mention it at all. The Bootstrap paradox is not a contradiction. Under Novikov, under Deutsch, under self-consistency, it is perfectly allowed. The loop closes. Nothing is inconsistent. And that is exactly what makes it so unsettling. The grandfather paradox threatened too much change. The Bootstrap paradox threatens something deeper. Information, structure, even meaning, appearing with no source, sustained by nothing but its own consistency. Some who write about this draw a bold conclusion, that the Bootstrap loop shows things can exist without any origin at all, with no first cause required. Hold that conclusion carefully. We will examine it, because it does not say what its proponents think it says. And there is the crack we were told to keep in mind. The multiplicity problem. Classically, every initial condition admits infinitely many self-consistent histories, and there is no rule to select which one happens. The philosopher John Earman pressed even further, arguing that the self-consistency constraint might impose no restriction at all outside the looping region, while inside it the constraints could remain genuinely paradoxical in ways no one has resolved. So the principle that seemed to rescue us from contradiction leaves a vast silence at its center. Something selects one history from infinitely many. The physics does not say what. The equations describe the consistent loops. They are mute about why this loop, rather than any of the others, is the one that is real. There is something in this that the oldest stories already knew. In the myth of Oedipus, a prophecy foretells that a man will kill his father and marry his mother, and every action taken to prevent it, the abandonment, the flight, the avoidance, turns out to be precisely the action that brings it about. The structure is a self-consistent loop, 2,500 years before the Cauchy problem was written down. The effort to escape the outcome is the mechanism of the outcome. Under Novikov, this is not a tragedy imposed by a cruel god. It is geometry. The only history that exists is the one in which the prevention causes the very thing it meant to prevent. When I sit with that, what unsettles me is not the loss of the ability to change the past. It is how completely the picture closes. There is no slack in it, no spare room, no unwritten margin. Every act fits, because only the acts that fit occur. And a reality with no slack, a reality in which everything, down to the last glancing blow, coheres with everything else, does not behave like the output of blind chance, which is sloppy, wasteful, strewn with dead ends. It behaves like something composed. What does it mean that the deeper we follow the logic of self-consistency, the less the universe resembles an accident, and the more it resembles a finished sentence, in which every word was chosen so that the whole would pass? For the past stretch of this exploration, I have presented what the physics permits and what its architects claim, as fairly and as fully as the evidence allows. I have not yet tested any of it. That was deliberate, because woven through this elegant structure are several claims that quietly step beyond physics. Claims about freedom, about origins, about whether the universe needs anything outside itself to explain its own consistency. Those claims have been stated by serious people as if the mathematics settled them. It does not. Now we examine whether they survive. Begin with the phrase that has been waiting since we first met it. Nature finds a fixed point. The universe fights back against paradox. The timeline self-corrects. This language runs through popular accounts of the Novikov self-consistency principle, and it is worth noticing how much work it does. It paints the universe as an agent, watchful, purposeful, reaching in to prevent contradiction, jamming the gun, nudging the billiard ball, curating its own consistency. It is a vivid picture. It is also, examined closely, empty. Look at what the physics actually says, stripped of the personification. There is no force in the Novikov principle. The research is explicit. Consistency is a global boundary condition, not a local push or pull on the traveler. Nothing reaches in, nothing intervenes. The paradoxical histories are not stopped. They are simply not among the solutions that exist. To say the universe finds a fixed point is to smuggle a mind into a description that contains no mind. And the physicists who use the phrase know it. Recall the admission from Scott Aaronson and John Watrous. They asked how nature finds the consistent state, and then conceded that the issue is admittedly mysterious. Stephen Hawking named his mechanism the Chronology Protection Agency, and he was joking, precisely because everyone understands there is no agency in the equations. The personification is a figure of speech papering over a blank. So the materialist faces a clean fork, and neither path is comfortable. Either the universe genuinely curates its own consistency, in which case you have attributed foresight, selection, and purpose to unconscious matter, which is the very thing materialism exists to deny, or there is no curating agent in the physics at all, in which case the consistency of the world is a brute, unexplained fact that the equations describe but do not produce. What does it mean that the only natural way to talk about the principle is to credit the universe with a mind, and that the moment you remove the mind, the explanation evaporates? The language is not careless, it is a confession. The order looks authored because describing it without an author requires words the physics cannot cache. Consider how this kind of language works elsewhere, and how quickly it dissolves under inspection. We say water finds its own level, but water does not search for anything. It falls, and where it stops is only the shape of the container and the pull of gravity. We say the timeline protects itself, and we have done the same thing. We have described a result, the consistency, and disguised it as an action, the protecting. Strip the disguise, and the result stands there, naked and unexplained. The world is consistent, and nothing in the equations makes it so. A thermostat holds a room at a set temperature because an engineer built into it a goal and a mechanism to pursue that goal. The Novikov principle holds the universe free of contradiction, with no mechanism that pursues consistency and no goal written anywhere in the mathematics. And yet the goal is met perfectly every time, in every loop. Remove the engineer from a thermostat, and you do not get a cheaper thermostat. You get a device that maintains a temperature with nothing inside it doing the maintaining. That is not a simpler explanation. It is a deeper mystery, and the mystery has a shape. The shape is a result that behaves as though it were aimed at in a system that contains nothing to do the aiming. This brings us to the deeper claim, the one drawn from the block universe. If the past already exists, fixed, as real as the present, then, some argue, everything is settled. Free will is an illusion, and a history locked in 4 dimensions has no room for genuine choice and no need for any purpose directing it. The timeline simply is what it is. On this reading, eternalism plus self-consistency equals a closed, meaningless mechanism. And there is no creator authoring the story because there is no story being authored, only a block that sits there. The astronomer J. Craig Wheeler put the strong version bluntly. If time machines exist, he wrote, there can be no free will. You cannot will yourself to kill your younger self. Somehow, circumstances will dictate that you cannot behave in a way that leads to a paradox. State the argument fairly, and then watch it fail on its own terms. Its central move is to slide from a claim about time to a claim about freedom. From the past exists to nothing could have been otherwise. But that slide is a known error, and physicists themselves have flagged it. The block universe does not entail determinism. As one analysis in the physics literature puts it bluntly, the inference from the block universe to the absence of free will is now generally recognized as a fallacy. The 4-dimensional block exists whether the events within it are produced by deterministic laws or by indeterministic ones. Eternalism says the future is real. It does not say the future is forced. A block universe can be threaded by genuine chance, by genuine choice. The block simply contains those choices as part of its fabric, rather than erasing them. And there is a second confusion underneath the first, one that classical theism untangled centuries before relativity. The argument assumes that if a history is fixed and fully known, it must be coerced. But knowing is not causing. That a complete history exists and is even known in full by a mind outside of time does not mean that mind reached in and forced each act. Foreknowledge is not determination. Picture a historian reading the finished biography of a life long over. Page after page, she knows exactly what the subject will do next, every choice, every turn. Her knowledge is total. And her knowledge causes none of it. The man in the biography chose freely. The historian merely sees, all at once and after the fact, what he chose. To confuse the reader's foreknowledge with authorship of the deeds is an elementary mistake. And it is precisely the mistake the block universe argument makes when it slides from a timeless mind that sees the whole to a tyrant that dictates each part. A fixed timeline, on the theistic reading, is not a prison. It is a finished work. Every free act of every agent already woven in, seen whole by the one who is not bound by the sequence. The block universe, far from abolishing such a mind, is exactly the structure that a timeless intelligence would survey at once. The eternalist picture does not remove the author, it describes the author's vantage. What does it mean that the strongest argument against purpose in this whole subject turns out to rest on a fallacy its own field has already named? It means the conclusion was never carried by the physics. It was imported and then dressed in spacetime. Now to the Bootstrap paradox, the loop with no origin, and the boldest claim of all, that information and objects can exist with no source, uncaused, self-sustaining, and therefore that the universe needs no first cause. A proof that no one proved. A watch that no one made. If a thing can simply exist because it exists, the argument runs, then the demand for an origin, for a cause behind existence itself, dissolves. This is the claim that, examined, turns most sharply against the hand that wields it. Grant the loop entirely. Grant that within it no event is the first, that the proof and the watch have no internal origin. Notice what you have not explained. You have explained nothing about why this loop exists rather than no loop at all. The proof loops, fine, but the entire looped structure, the whole self-consistent package, did not have to exist. It is contingent. It could have been absent. And a contingent whole, however cleverly it tucks its ends together, still demands a sufficient reason for being rather than not being. Asking who wrote the proof inside the loop is the wrong question. The right question is, why is there this loop, this information, this watch, this universe at all? The loop answers the first question by saying no one. It cannot answer the second by saying anything. And here is the inversion that the proponents never see coming. An entity that exists by its own nature, uncaused, dependent on nothing outside itself, self-sustaining, origin-free, is not a novel discovery of time travel physics. It is the oldest concept in classical theism. Philosophers have a word for that mode of existence: aseity, existence from itself. And for 2,000 years, it has been reserved for exactly one thing: the uncaused cause, the necessary being that depends on nothing. The Bootstrap paradox does not abolish the first cause. It accidentally rediscovers its defining attribute, and then tries to pin that attribute on a wristwatch. But a wristwatch is contingent. It is the kind of thing that needs a cause. To make it self-existent, you would have to give it the very property that only an uncaused, necessary reality can possess. The argument meant to remove God, instead, smuggles in God's signature and staples it to a prop. Even the physicists feel the strain. The research notes the bootstrapped loop appears to conflict with the conservation of information and with the second law of thermodynamics, the principle that ordered structure does not assemble itself from nothing. Information from nowhere is not a solved problem in physics. It is an open wound. Press the point one more turn because it matters. There are only two ways a thing can exist. Either it depends on something else for its existence, in which case it is contingent, and we may always ask what it depends on, or it does not depend on anything, in which case it exists by its own nature, necessarily, and the question of its cause does not arise. Classical theism has always said that all the furniture of the world, every star, every particle, every watch, belongs to the first category, and that the chain of dependence must terminate in exactly one reality of the second category, an uncaused, necessary being. The bootstrap loop does not escape this division. It takes a contingent object, a watch, a proof, a person, and tries to grant it the second kind of existence, existence with no dependence and no origin. But you cannot promote a contingent thing into a necessary one by bending it into a circle. A loop of dependent things is still a loop of dependent things. Coiling the chain does not remove the need for a floor to rest it on. The only thing that can ground a contingent loop is something that is not itself contingent, not itself inside the loop, not itself in need of a cause. The bootstrap paradox, far from abolishing that something, is the most vivid illustration in all of physics of why it is required. There remains the escape hatch some reach for when self-consistency feels too confining, the many worlds interpretation. Perhaps, the argument goes, there is no single self-consistent history at all. Perhaps the traveller who kills the grandfather simply branches into a parallel universe where the deed is done, while the original timeline rolls on untouched. The paradox dissolves because every outcome happens somewhere. But weigh what this purchases, and at what price. It resolves a paradox we have never observed by invoking an infinity of universes we can never observe, measure, or detect. No branch other than this one has ever been seen. The theory is unfalsifiable by construction. It is not a measurement. It is a metaphysical preference, chosen precisely because it avoids a conclusion. They accuse the theist of inventing an unseen reality to fill a gap. But what is an unobservable infinity of branching worlds, summoned specifically to dissolve a paradox, if not a gap filled with the unseen? It is naturalism of the gaps, and multiplying universes to avoid explaining one is not parsimony, it is the opposite. And when every other resolution is pressed, the final retreat is always the same. We do not understand it yet, but a future theory of quantum gravity will. Maybe quantum gravity will tell us whether closed time-like curves can form. Maybe it will tell us which of the infinitely many consistent histories is the one that happens. This is not an argument. It is a promissory note written against a discovery that may never arrive, and it is worth naming as such. The selection of one actual history from infinitely many consistent ones is not the kind of gap that a better equation closes. It is a why question, wearing the mask of a how question. Even with a complete theory of the mechanism, the question of why this history is the real one, and not one of its infinite consistent rivals, would stand exactly where it stands now. There is a tell in how this promise is always phrased. It is never, "We will explain why one consistent history is real." It is always, "We will understand the mechanism better." The substitution is quiet and constant. A how is offered in the place of a why, and the listener, hearing the word explain, assumes the why has been handled. It has not. Consider a locksmith who can describe every spring and tumbler in a lock, the full mechanism, flawless and complete, and who has told you nothing about who cut the key or why the door was ever built. The mechanism of self-consistency, even fully known, would be that lock, a perfect account of how the loop closes, and total silence on why this loop, out of all the consistent loops, is the one the universe actually contains. To wait for physics to answer that is to wait at a window through which the answer was never going to come. Which returns us, finally, to the crack at the center, the multiplicity problem. Because it is not only the deepest difficulty in the physics, it is the place where the evidence, followed honestly, points past the physics altogether. Recall the finding: for a single billiard ball, infinitely many self-consistent histories exist, and the classical laws contain no rule whatsoever to select which one is real. The sum over histories assigns each consistent extension a well-defined probability. But probability is not selection. Something settles on one history out of an infinity of equally consistent candidates is the one that actually occurs. Sit with the structure of that. The physics gives you a field of possibilities, all internally consistent, all permitted, and then falls silent at the only question that matters: why this one? This is the same shape we meet at the deepest level of every fundamental question. A space of possibilities that could have been otherwise. A single actuality selected from it, and no mechanism within the system that performs the selection. Precision requires decision. Selection requires a selector. A universe that presents infinitely many consistent histories and realizes exactly one is not displaying the blind indifference of matter. Matter has no stake in consistency. A pile of unconscious particles does not prefer the history that closes over the histories that contradict. The preference for the whole, the consistent, the single realized world, is the fingerprint of a mind that chose it. And the selection is not the only fingerprint. Look back at the thresholds the physics insisted on, the precise edges where loops become possible at all. A Tipler cylinder admits closed, time-like curves only when its surface exceeds roughly half the speed of light, only above 10 solar masses, only at near neutron star density. Exact conditions, not approximate ones. Gödel's rotating universe locks its rotation, its cosmological constant, and its density into a single rigid relation, each quantity fixed in proportion to the others. A wormhole holds open only when the energy condition is violated by an exact amount, on an exact inequality. Wherever this subject brushes against the possibility of a loop, it meets not vague tendencies, but sharp, law-like, numerically precise structure. That precision is itself evidence. A universe whose every exotic possibility is gated by exact thresholds, and whose every realized history is globally coherent, is exhibiting the two things unconscious matter never produces on its own: exact order and coherence across the whole. Precision requires decision. We meet that pattern here in the physics of time loops. Exactly where we meet it, everywhere else the questions run deep. This is the part that stays with me. Not the time loops, the selection. A reality in which paradox has probability zero, in which every actual history is globally whole, in which one consistent world is chosen from infinitely many, is not a reality that holds itself together by accident. Consistency is not free. Unconscious matter does not enforce it, cannot select for it, has no reason to prefer it. A universe that cannot contradict itself looks exactly like a universe authored by a single intelligence that cannot contradict itself. A reality held in one coherent thought. The Novikov principle says the timeline never produces a contradiction. The honest question is not how the timeline manages this. It is who holds a reality so that contradiction has nowhere to occur. The evidence, examined without flinching, points in one direction. Not to a universe that fights back, for there is no fighter in the equations. To a universe that was authored whole, by an intelligent cause with the power to set the laws, the knowledge to span all of time at once, and the will to select, from infinitely many consistent histories, the one that is. These are not three vague compliments paid to a mystery. They are the precise attributes the physics itself keeps demanding and cannot supply on its own. Something to set the exact thresholds. Something to hold all of time as a single coherent whole. And something to choose one consistent history where the equations offer infinitely many and select none. That is not the end of inquiry. It is where the inquiry, when its own loose end is followed, actually leads. Let me bring this exploration to a close. We began with a man who could not change the past and asked why. We followed the closed Timelike curve out of Gödel's rotating universe and Van Stockham's spinning dust, through Tipler's cylinder and the Morris and Thorne wormhole, into the formal Novikov self-consistency principle, where paradox carries a probability of exactly zero. We watched the grandfather paradox dissolve into a billiard ball's glancing blow, and then split, in the quantum realm, into the rival models of David Deutsch and of Lloyd and McCone, tested in photons at Queensland and Toronto. We weighed Stephen Hawking's chronology protection against its own author's later doubts, and we found, at the centre, a bootstrap loop with no origin and a multiplicity of consistent histories with no rule to choose among them. Then we tested the claims that had been quietly attached to all of it. The universe that fights back turned out to have no fighter in it, only a mind smuggled in by metaphor. The block universe that abolishes free will turned out to rest on a fallacy physics itself has named, and to describe, rather than remove, the vantage of a timeless author. The bootstrap loop that needed no first cause turned out to rediscover the first cause's own defining attribute, and misattribute it to a watch. The many worlds escape turned out to be the unseen invoked to avoid the obvious. And the selection of one consistent history from infinitely many turned out to be no gap a future equation will close, but a decision, and decisions require a deciding mind. This is the rational conclusion, and I will state it without hedging. A reality in which contradiction has probability 0, in which every loop is whole, and one consistent history is chosen from an infinity of them, points not to blind matter, which has no stake in consistency, but to an intelligent cause, eternal, uncaused, self-existent, in the only sense that word can truly bear, holding the whole of time in a single, coherent thought. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. We treated the time traveler here as one self on one history. But there is a rival picture, the one that says the loop never closes on a single timeline at all, that the past does not stay whole, but splits into a superposition, branching into outcomes that all occur. If that possibility unsettled you when it surfaced earlier, I have followed it much further, into the quantum model, where your own past becomes a blur of coexisting versions. You will find where on the end screen now, and in the description below. So, the next time you imagine reaching back to change one moment, and feel certain you could, sit with what the equations quietly insist. The gun was always going to jam. The blow was always going to glance. The loop was always closed. And a universe that was, in every thread, always already whole, is not the kind of thing that holds itself together. It is the kind of thing that was held. Good night.